All right, we're on section 14.2 with stoichiometric calculations, and this is kind of the heart of this chapter. So I've taken and broken this section down into two parts. We'll just do, you can just watch the first part now and then the second part the next day. But focus on this, make sure you understand what's going on. I'll try to make just a few examples that you can kind of really follow, and then but watch it again if you need to so that you understand what's going on here. As far as objectives, these are the kind of the key things. Be able to explain the importance of balancing equations when we do these ratios. These should be mole ratios. Determine mole ratios in chemical equations. Calculate the number of moles, whether we're talking about reactants or products, based on a balanced equation. And finally, and probably the most important, be able to calculate mass. So whether we're talking about reactants or products, but in a balanced equation, you need to be able to do that. That's what it's all about. Okay, so first of all, what do they talk about when they're saying mole ratios? Well, a mole ratio is the relationship between two parts of a chemical reaction. So two different compounds or elements that are in it, the relationship between. So for instance, if we have this equation, 2H2 plus O2 yields 2H2O, we're talking about two parts. So it could be this hydrogen, it could be oxygen, it could be hydrogen and water. We're talking about the mole ratios. And so if we look, these numbers out front, those are our mole ratios. And if there's no number out front, that's a 1. Okay, so here's what we're saying. 2 moles, and we could be talking about molecules too, as like I said in the last section, but 2 moles of hydrogen are equivalent to, and I usually kind of do a little squiggly equal sign, equivalent to 1 mole of oxygen. And what we're going to do is we're going to use those and we're going to make some fractions with those. So we're going to say, hey, we could have 1 mole of O2, over 2 moles of H2O or H2. Or we could do it the other way around. You could say 2 moles of H2 over 1 mole of O2 based on which way we need to go. Okay, so we've got those ratios. You could also do hydrogen and water, so you could say 2 moles hydrogen is equivalent to 2 moles of H2O, and you could set up your fractions. In this case, 2 over 2 gives you, doesn't really do anything, but it does convert what these things are, and that's going to be important. In this chapter, doing stoichiometry, you really want to make sure that you keep your labels. This is where labels become very important. Okay, so if we look at this one, think of the mole ratios that we could write. We could say 4 moles of aluminum is equivalent to 3 moles of oxygen, or vice versa, 3 moles O2 over 4 moles of aluminum. So I'm just taking my coefficients, and these have to be balanced. That's why balancing it is so important. That's one possible one. I could do 4 moles of aluminum with 2 moles of Al2O3, aluminum oxide, or vice versa, 2 moles Al2O3 with 4 moles of aluminum. And we're not going to worry about reducing. It's not worth it. You can just do it while you're doing punching things into the calculator. Let the calculator take care of it. So don't worry about reducing things down. And then there's a third one we could do with oxygen and aluminum oxide. So you could say 3 moles of O2 is equivalent to 2 moles of Al2O3, and vice versa, 2 moles of Al2O3 to 3 moles of O2. So what we've done is we have come up with, in this case, if there's 3 different things, 3 different items in here, we were able to write 6 different ratios that we can do, 6 different relationships between moles that are in here. They're always dependent on the coefficients out front when we write these mole ratios. All right, so now let's try to go another step and say, why are we doing this? What do we care? Why do we care about this? You know, here's what we're going to do. We want to be able to make mole calculations based on this balanced equation. So let's say that we had 0.5 moles of magnesium hydroxide. So we've got 0.5 moles of that. And we want to know how many moles of phosphoric acid are we going to need. Okay, so we're trying to find, how many moles we have there. So we need the relationship between these two. So we have two possibilities. We could have 2 moles of H3PO4, that's the phosphoric acid, over 3 moles of MgOH2. Or we could do vice versa. We could say 3 moles MgOH2 over 2 moles H3PO4. All right, so always, do what are you trying to find? Do our little question mark. This is coming back. We're going to do this all the time now. We want to know how many moles of H3PO4 we can have. How many moles H3PO4 if I have 0.5 moles of MgOH2. Now think about, we've got to get the moles of magnesium to cancel, magnesium hydroxide, and we want to end up with moles of H3PO4. Remember we talked about before that the one we want to get, what we're trying to get to, we want on top. So if we look at these two possible fractions that we want to use, you can see that we want to use the top one because we're trying to find phosphoric acid, H3PO4. So actually it's kind of nice. So I'll just write that little time sign in there. And so we're going to do that. So we would take 0.5. Now, what I've always said, if it's on top, we multiply. If it's on the bottom, we divide. So take 0.5 times 2 divided by 3. So it would be 1 divided by 3, or 0.33 moles of H3PO4. Okay? So you're looking at your two ratios between where you're starting. So we were starting with MgOH2. We're trying to get moles of this one, and then we're looking at the ratio between them. In this case, it's the coefficients 2 and 3, and we want the one we're trying to find, phosphoric acid, on top. That's this one right here. So we're going to put that on top. We're going to put the other one on the bottom. Notice that this would cancel with that. If it doesn't make sense here, put this over 1 so you kind of can see that. It's because I'm a little bit off, but that's how it works. Okay? All right, so I want you to see if you can figure out this one. How many moles of sodium oxide, okay, so we're looking for this one right here. How many moles of sodium oxide can be formed if we have 2.36 moles of sodium nitrate? So we have 2.36 moles of that one. We want to know how many moles of this one we have. There's our coefficients that we're going to use. Stop the video and do this problem. Okay, so I'm going to say, hey, how many moles of sodium oxide, Na2O, equals, what am I given? 2.36 moles of NaNO3. Now, you guys might look at this and say, oh, this is pretty easy. I can do this stuff. I can do this in my head, Well, yes, this is just the very beginning. This is just a one-step problem, and we'll do usually, most problems are going to be 3 steps, and occasionally we have some other things that go along with it. So do it this way. Write it out. I can't stress that enough. So if we want to figure this out now, we want moles of what we're looking for on top. So that's Na2O. We're going to use that coefficient. So we're going to say 6 moles Na2O. And what we're looking for, or what we want to cancel now, is going to go on the bottom. And that was our NaNO3. So we're going to say 2 moles of NaNO3. And now if you want to, you can reduce down. But like I said, usually it's just simpler to do it on the calculator. Take your 2.36, take that times 6 divided by 2, and you end up with 7.8 moles of Na2O. Hopefully that's what you got. Alright, that's the end of the first part. So that's probably enough right now, and you can kind of stop the video and wait for the next part for probably tomorrow. Alright, we're starting on part 2 of this section, and this is kind of where we get to put it all together, and we're talking about mass to mass, and this is real. Up to this point, we don't have any scales or anything like that that measure mass. We have measure moles, but we have scales that measure mass, and so this is what we have to do when we're doing this. So, all right, so when we're doing mass calculations, these are things that we can determine. We can determine the mass of the reactant necessary to give us a certain amount of product. So, hey, I need 50 grams of this product. How many grams of this reactant? That's pretty much what factories do, and the chemical companies are trying to do this. They do that all the time. I can figure out the mass of the product that would be produced from a given reactant. So if I kind of reverse that last problem, say, hey, if I have this much to start with, how much am I going to get at the end? And the last one is that we really would try to do is say, well, if I've got so much of this reactant A, how much of reactant B do I need in order to make this thing go? And those are kind of the 3 different things that you would do in real life problems, in real life situations if you were, working in industry trying to calculate some of this stuff. All right, there's 4 steps that we're going to follow as we do these problems. First step, and this is why I really stress being able to balance equations, is you got to have the balanced equation. If you don't have it balanced, you're not going to get it right because you won't have the right mole ratio. So number 1, balance the equation. Number 2, we've got to change to moles. Step 1, change to moles. Okay, that's what we always do. So if it's not given in moles, in the last part of this one, we were doing everything was started with moles and ended with moles. Well, there you don't have to do this step, but normally we start with grams, and then the first thing you got to do is convert to moles. Next step is, okay, we've now converted to moles of what we knew, what was given. I always call it the given. They call it the known. And then we're going to have to convert to moles of what we're trying to find, or the unknown. What are we trying to get to? We got to convert to those moles. And then the last step is convert from moles of what we're trying to find, moles of the unknown, to, it says the requested unit, whether that's grams. We could be finding liters, we could be finding volume, we could be finding particles. Most likely 99% of the time in real life. I won't say even that much maybe, but most of the time you're going to be doing grams. You could be liters, you could get quite a bit in real life examples. Probably not going to count particles, but those other ones, yes. All right, let's do this example. Pentane, C5H12, reacts with oxygen gas to produce carbon dioxide and water. How many grams will be produced by the reaction of 108 grams of pentane? And I'm going to add in a new page and add it on there so we got a little more space to work on this. Alright, so we're using pentane, C5H12, and we know that we're burning it. So we've got O2, and we're going to get carbon dioxide and water. This is a combustion reaction, just like what we did in the last chapter. So, balancing it, let's put a 5 here to balance the carbons. Let's put a 6 here. That makes 10 oxygens on there, and 6 more over here. So 16. So we would put an 8 right there to balance that equation. So now we've got a balanced equation. So that was step number 1. All right, so now we were given 108 grams, and we want to find how many, what were we trying to find? How many grams of CO2, and we were given 108 grams of C5H12. Okay, so step number 1 is convert to moles. So in this example, we need to check this. Okay, and we're going to, if you remember the mole map, we need a mole, 1 mole C5H12. Don't lose your labels. And if we want to add it up, 5 times 12 plus 12 times 1. So we got 60 and 12, so 72 grams of C5H12. Thank you for writing that label down. Then the next step was change from moles of what we were given, moles of the known, so in other words moles of C5H12, to moles of CO2. And remember, I always said, hey, the one we're trying to find goes on top. So we're looking at mole ratios. So there's our 5 for CO2 and just a 1 here. So I would say 5 moles of CO2 and 1 mole of C5H12. And our last step is to convert from moles of CO2 back to grams of CO2. Well, CO2 would be 12 plus 2 times 16, or 44 grams. And I'm running out of space, so on top would be 44 grams of CO2, and on the bottom would be 1 mole of CO2. Okay, so CO2 here. And if we cancel, just check this out. These cancel. Moles of C5. They have to be the same. If you just put moles, we don't know if they're C5 or CO2. If you don't write your labels, you will flip these. Okay, almost guarantee it. That cancels. I'm left with grams of CO2. So now all I got to do is I got to do all my math. So I'm going to put in 108. So 108. Take it divided by 72, and then times 5, and then times 44, and I get equals 330 grams CO2. Now, if that didn't make sense, go back and watch that part again, because this is such a crucial thing. This is the key thing in this chapter, to be able to do gram to gram calculations on a balanced equation. So make sure you know how to do that. All right, I want you to try this one. So we've got a thermite reaction, which is always really interesting. Burns really, really hot. Thermite can burn right through steel and things. Between aluminum and iron 3 oxide, so we got to make that compound, produces aluminum oxide and iron. Looks like a single replacement reaction. If we have 500 grams of iron, how much iron 3 oxide would be used? So I want you to work this problem on your own. Stop the video, do this one. I will, in a little bit, if you want to see if you have the equation right, I'll do the equation, then I'll kind of give you a break again, and then I'll do the last part of it. So go ahead and do that. Alright, if you want to double check your reaction, because you got to get your balanced equation right, and if you don't have that right, you're not going to be able to do the other part. So if you want to check that, this is it. Otherwise, if you're just doing that, hit the stop and do the last part of it. Well, so here's our beginning. We're trying to find how many grams of Fe2O3 given 500 grams of Fe. First step, change to moles. So 1 mole of Fe over its molar mass, 55, I think, 0.85 grams Fe. And now we do mole ratios, so we're trying to convert from moles of iron to moles of what we're trying to find, Fe2O3. So we're looking at the coefficients. We're looking at those coefficients. Making the one we're trying to find, that's this one on top. 1 mole Fe2O3, 2 moles Fe. Then, once we've got moles of that, we need to convert back to grams. So we need to figure out the molar mass of Fe2O3. So that'd be 2 times 55.85 plus 3 times 16. Okay, and let's see, that would be 159.7 is what I get, grams. So that's Fe2O3. So I'm going to make that on top, 159.7 grams Fe2O3 over 1 mole Fe2O3. Please go back and check now. Do your things cancel? Does everything cancel? Moles of Fe cancel. Moles Fe2O3 cancel. I'm left with what I'm trying to find. All right, good enough. Now we can do the math. 500 divided by 55.85 divided by 2 times 159.7, and I get 714.9 grams Fe2O3. Wow. All right. Now, once again, if that doesn't make sense, go back, watch that video again. Okay? It will start to make sense as you figure out what's going on here. Focus on what I'm doing, and you need to be able to do these kinds of problems. You know, at this point, you need to be able to do problems like this. Okay? All right. So, somebody else feels your pain here, but here's the end.